When you hear the word sine or cosine, you probably think of wavy graphs or trigonometry formulas. These curves appear in math class, but where do they actually come from? They aren't just drawn out of nowhere. They originate from circular motion. More specifically, from a single point rotating around a unit circle. But the question is, how are they connected to the unit circle? In this video, we'll explore how sine and cosine emerge directly from that rotation on the unit circle. We'll start with the unit circle, examine the coordinates of the moving point, and then trace how these coordinates form the sine and cosine waves. Let's begin. We begin with the unit circle, a circle with a radius of 1 centered at the origin of the coordinate plane. Imagine a point moving around the circle in a counterclockwise direction. At any position, this point has coordinates x, y, and these coordinates change smoothly as the point rotates. The x-coordinate represents the horizontal position, and the y-coordinate represents the vertical position. With radius 1, the y value gives us sine, and the x value of the point gives us cosine. This gives us the coordinate of the point, cosine theta, sine theta. As the point rotates, we'll track how these coordinates evolve, starting with the y values, which lead us to the sine function. Now, to draw the sine graph, let's have a fresh coordinate plane. Here, the axes are a bit different to the unit circle. For the horizontal axes, we will have the theta, the angle on the unit circle. Then for the vertical axes, we will map the sine value at the given theta, which is the y-coordinate of the point on the unit circle. This allows us to define the function y equals sine theta, which shows the change of sine values as the theta on unit circle changes. At the start, with 0 degrees, y equals 0. As the point rotates from 0 to 90, the y value gradually rises until it reaches 1. Then from 90 to 180, it decreases back to 0. Then it dips down to -1 and returns to 0 by 360. These gradual, continuous transitions create the smooth curve of the sine wave. There are no jumps because rotation on the circle happens at a constant rate. It rises from 0 to 1, falls to 0, drops to -1, and returns again to 0. That means the wave pattern repeats every full rotation of the circle. But what happens if we rotate beyond 360? The answer is simple. The point simply loops around the circle again. The same pattern of sine values repeats because the position of the point starts repeating. So the sine wave also continues repeating beyond 360 and before 0 into negative angles. This repetition is what makes sine a periodic function. If we rotate in the opposite direction, clockwise, we define those angles as negative. At -90, sine is -1. At -180, it's back to 0. At -270, it's 1. And at -360, it completes the loop and returns to 0. Negative angles trace the same wave, just backwards. So, the sine function is continuous at all theta, values periodically moving between -1 and 1. Therefore, the domain is -infinity to infinity, and the range is -1 to 1. This symmetry helps us understand and predict the sine wave for any angle positive or negative. Now let's shift our focus to the horizontal position, the x value of the rotating point. Here, be careful with the mapping of unit circle to wave function. Unlike sine where the vertical height of the point directly maps to the wave height, cosine comes from the horizontal distance. This can be harder to visualize because we typically graph wave height on a vertical axis, but cosine still follows from the x-coordinates of circular motion. As the point rotates, the x value starts at 1, decreases to 0, reaches -1, and returns to 1 by the end of a full circle. If we plot these x values over angle, we get the cosine wave. The key difference is the starting point. Cosine begins at its maximum value, whereas sine begins at 0. The cosine wave has the same smooth, repeating shape as the sine wave, but it's phase shifted. It's essentially the same curve, just shifted to the left or right. Therefore, the domain and range remain the same as well, negative infinity to infinity and minus 1 to 1. Now that we have these, we look at the defining properties that allows us to describe a wave graph. Let's use the sine graph for this explanation, keeping in mind that the cosine would be the same. We'll also switch back to the standard variables, x for the horizontal axis and y for the vertical one, since this is the usual convention for functions. The first characteristic is that the pattern repeats itself as we saw before after certain values. We call this the period, which is of 360 degrees. You will usually see it from maximum to maximum or minimum to minimum, but this is a constant between corresponding points of each repetition. Now recall that the range is minus 1 to 1, so the wave is trapped between the line y equals minus 1 and y equals 1. We can use this to find a line that divides the wave. We call this the principal axis, which has equation y equals 0. Note that this line is at the same distance from either maxima or minima. This distance gives us our last characteristic when describing a wave, the amplitude, which in this case is 1. As you may have seen with other functions, with this wave graph as a base, we can create other types of waves. But they will all have periods, principal axes, and amplitudes. To summarize, a point rotating on the unit circle gives us both sine and cosine. The vertical position forms the sine wave. The horizontal position forms the cosine wave. Both functions are smooth, continuous, and periodic. They repeat every 360 or 2 radians. The amplitude is 1 and the period is 360 because we are using a unit circle. This circular foundation gives sine and cosine their exact waveforms, step by step, from rotation alone. This video is brought to you by LightHouse Global, your personal online tutoring for IB, college applications, and school subjects.